Any questions on homework? No? All right, let me go through some stuff that's in the video if you watch the video and stuff, but I just want to kind of get our brains going again. I know it's a Monday. Comparing the graph of a function to its derivative. So if we have a function, in this case it's the function 3x, it's a line, then the slope of the tangent line at any point on this graph would be what? It would be constant, it would be 3, wouldn't it? So if I were to actually show you the derivative should be constant 3, right? No matter where I am on that line, the slope of this little tangent line is 3, so we represent it up here with a 3. And so that stays the same the entire time. If I change this function to something like a quadratic function, and I move this thing around, then look at the slope. Over here, the slope is like 4.6. Over here, the slope is 1.8. Right here at the origin, looks like the slope would be about 0, right? And then over here, my slopes would be negative. So if I graph the derivative, you can see that, let's say at this x value, I have negative 2.46, so I put down here 2.46, I put a dot. If I move this over, it's still negative, but it's smaller, so it's getting closer and closer to 0. And once you get past 0, your derivative is positive. And we can just keep doing this for all these different types of graphs. And that's part of what your homework was about. So now, some notation. Anytime that we have a function, y is equal to f of x, then there's different ways for me to tell you to find its derivative. I can write f with the little prime mark. That means the derivative. I could also write y with the prime mark. That would be find the derivative. I could write dy dx. Okay, dy dx means take the derivative. I could put df dx because f is the function. This is like the derivative of the function treating x as your variable. Or you could write d dx of f of x, which would mean take the derivative treating x as your variable of the function f of x. Then we use capital D and capital D. This will come up in Cal 3 if you ever have to take Cal 3. We use that notation instead. So all of those notations are the same, but there's one particular notation that's very useful, and that's this notation with the dy dx. It's called Leibniz notation. It's named after this guy who was one of the co-founders of calculus. The other founder of calculus was Isaac Newton. All right, so we'll use that extensively in this class. Now, in order for us to say a function is differentiable, that means that the derivative has to exist. Now, remember, the derivative comes, to take a derivative, you have to do a limit, don't you? The limit, h goes to 0, f of x plus h, all that. There were two different formulas for it. Since it's a limit, we saw when we first studied limits, limits can sometimes not exist, right? If the limit does not exist, then that means the function, the derivative, does not exist. So it is possible for a function to not be differentiable at a certain point. If it is differentiable at a certain point or on an interval of points, then we say that it is differentiable on an open interval if the derivative exists at every point in that interval. Now, we also talked about continuity, that a continuous function is one that you can draw without picking up your pencil. Anytime a function is differentiable somewhere, it must be continuous there. So differentiability implies continuity. But be careful, just because it's continuous does not mean that it's differentiable. I'm not going to get into that too much, other than to say don't get those mixed up. Don't get the order of those backwards, all right? All right, so when do functions fail to have derivatives? When do the derivatives fail to exist? We talked about this last time. Anytime there's a cusp or a corner, your function does not, the derivative doesn't exist. If there's a jump or a vertical tangent line. So here's a corner. If I move the derivative, watch what happens. Right now the derivative is 1, isn't it? and then I get to this corner, and then right after that, right at the corner, it jumps. See how abruptly it changes? If I show you the derivative over here it was 1, right? And then when I get to that point right there, it jumps down to -1. And because there's a break in that derivative, the derivative doesn't exist there. All right? The other picture here is a jump, and the same thing. You can see if you look at the derivative of this one, there's a break in the derivative, so it would not be differentiable here at -1. And then the vertical tangent. Why is it not differentiable at a vertical tangent? What's happening to the slope of the tangent line here? Yeah, it's trying, your line here, your slope is starting to get bigger, right? 3.1 or 3.31. And then as I go a little bit closer, well, that's not going fast enough. See, now it's at 10, now 12, 60. Wait, I went past it. 60, 70, 80, 90. It's trying to become vertical, and so you can never have, when you talk about vertical lines, the slope of a vertical line is undefined. So therefore, the derivative is undefined or does not exist there. All right? So those are the three things that we have to be careful with when we're talking about derivatives. Corners and cusps, jumps in the graph, and vertical tangent lines. All right? Now, we also talked about how if you take the derivative of a function, you get a new function, right? And since you get a new function, it's possible to take the derivative again. When you take the derivative of a derivative, it's called the second derivative. And then if you take the derivative of that, you get the third derivative. And then you take the derivative of that, you get the fourth derivative. And so there's some notation that we want to get used to. If you see the little prime mark, that means first derivative. 2 primes means second derivative. 3 primes is 3 derivatives. And then obviously you need to stop with the primes because you have like 20 primes out there. So what we do instead is we start writing the number, the derivative in a parenthesis, in the parentheses. So if you write f and then in parentheses 4, that means the fourth derivative, then fifth derivative, and so on and so forth. All right? Just be careful because if there's a difference between writing this and this, right? Major difference. This means take the fourth derivative of the function. This means take the function and raise it to the fourth power. Totally different things. So that's why we put this in parentheses. Now, the other notation, the Leibniz notation, if you want to talk about first, second derivatives, you have to use this notation. So the first one, dy dx, first derivative. If I want you to take the second derivative, I have to put d squared y dx squared. And notice that the 2 up here is offset from the 2 down here, right? The first 2 is on the d, the second 2 is on the x. Why did we do it that way? Do y'all know why we do it that way? What's the difference between me writing this like if I were to put that? Why is it that we offset these? It's not just for fun. What do you think this means compared to this? This right here is really dy dx, what? Squared. That's the first derivative squared. This means second derivative. Take the derivative and then the derivative again. Totally different answers. Understand? So that's why we offset the 2's so that you don't confuse it with this. So it's just a matter of making sure you don't do the wrong operation. If we want the third derivative, we write it this way, fourth derivative, fifth derivative, so on and so forth. Understand? All right, now one of the major results of this class is that we can talk about the position, the instantaneous velocity, and the instantaneous acceleration of a particle. of something that's moving. So let's just say I'm walking along here, right? I have a position, right? I'll start my watch. Okay, here we go. I start it. Time right now is 0. I click start and I start walking. I walk a little fast and then I slow down and then I start speeding up and then maybe I go backwards and then I start going this way again, right? At every point in time I have a position, don't I? I have a position at every point in time. If you have a function that tells you where something is at every point in time, then the first derivative tells you the velocity at every point in time, and the second derivative tells you the acceleration at every point in time. All right? That's the value of those two things, or the derivative and the second derivative. So that's what this says. If s equals f of t, so you have a function of t, we use t instead of x because t is good for time, right? If you have that position of an object, then the first derivative of that function we will call v of t is the instantaneous velocity, and then the second derivative, or the derivative of the velocity, gives you the acceleration. All right, then we're going to start 2, 3, but I want to get into this. I want to do an example of this. All right, how many of you have seen this before? D of t equals negative 16 t squared plus v naught t plus d naught. How many of you have ever seen that before, or it looked kind of familiar? This is a position function. It tells you where something is at every point in time, but it happens to be a very special one. This gives you the position of an object on Earth. If you throw it into the air, it tells you where it'll be at every point in time. Right? So we discovered a long time ago that if you have two objects on Earth and you drop them, that they should hit the ground. What? If I drop these, they should hit at the same time. So, oof, right? That kind of looked like they did, right? Maybe? No? They did. So what about this? What if I take the paper in the book and drop those? Which hits first? The book? Okay, I'll drop it on my foot so I don't make noise. I mean, that's pretty obvious that that's going to happen. Now, why did that happen? What is it? Is it the air, or is it that this is heavier? The book is heavier, or is it that the air? It has everything to do with the air, all right? Has nothing to do with the weight. On Earth, if you take air out of it, which is kind of dumb because you can't really take air out of it, but if you can take air out of it, all things on Earth should drop at the same rate. In fact, if I take this, if you think that it's because the book is heavier, and if I put the paper on top of the book, what should happen? If you think it's because the book is heavier, the book should separate away from the paper, shouldn't it? Right? If you think it's because it's heavier. So they went together. Now, the reason why they went together is because the book, moved the air out of the way, and so that the paper no longer had the air resisting it, so they fell exactly at the same rate. So it was discovered that if you take air out, all objects on Earth fall at the same rate, and this is the actual function that gives you where it is at every point in time. This is it. All objects on Earth fall with this equation. Now, the negative 16 comes from gravity. If you change the planet you're on, this number changes, right? So if you're on Earth, that number will change. Y'all have heard of the acceleration of gravity being like negative 9.8 meters per second or something like that, physics classes? If you convert 9.8 meters per second into feet per second, then you get this. So this is the same formula, but with feet in seconds instead of meters in seconds. So let me explain what everything is, and then let's talk about velocity and all that stuff, okay? So check this out. First of all, t here is equal to time, and it's always measured in seconds. V, with a little zero down there, we call that V naught. This is your initial or starting velocity. And this would be positive for up, negative for down. I'll explain that in just a second a little bit more. D naught is your initial height. Bless you. And that's measured in feet. So here's what this formula says. If I have an object on Earth, and I take the ground to be 0 feet, all right? Now I realize I'm on the second floor of a building, but let's just say the ground right here is 0 feet. Then if I raise this pen up 6 feet, then D naught, my initial height, is what? 6, right? If I just let it go, then the initial velocity would be what? That's acceleration. If I just let it go, I'm not giving it any speed, am I? Just letting it go. So the initial velocity would be 0, right? Does that make sense? So if you just take an object on Earth, raise it to a certain height, and let it go, the height you start with is D naught, and the V naught is going to be 0 if you just drop it. Now, I say it's plus for up, negative for down. So now let's say I take this pen, instead of just letting it go, I shoot it out of a little cannon, okay? So I've got it here, and then I go ready, set, go. And now I gave it an initial velocity up, right? Had to go up, and then comes back down. That V naught would then be a positive number, and they would have to tell you what it is, okay? Shooting it out of a gun, you have like muzzle velocity. It's how many feet per second, 1,000 feet per second is how fast the bullet comes out of the muzzle. Whatever. So that would be your V naught. Now I could also take this, and I could give it a velocity downward instead, and then you would plug in a negative number there. Got it? But in any scenario that I have there, it should follow that function. And does everyone realize that this is just a quadratic function? Right? It's just a quadratic function. The V naught and D naught are just constants. They're just numbers. I don't know what they are. Right? So if this is the scenario, then can you tell me what the velocity of the object will be at every point in time? What will it be? Well, I just told you, if you know the position at every point in time, then you can always get the velocity by doing what? Taking the first derivative, right? Taking the first derivative. So this would be d prime t, which for us right now would mean we would have to do the limit, right, as h goes to 0 of what we get when we plug in what into this. What was our definition for our derivative? The derivative at x was limit h goes to 0, f of x plus h minus f of x all over h, right? That's our derivative function, or that's our derivative limit definition. So we'd replace the x with t's, right? So because I'm using t's here instead of x's. So it'd be what I get when I plug t plus h in, minus what I get when I plug in t and then divide it all by h. And that looks like a freaking disaster, doesn't it? You have to do negative 16 t plus h squared plus v naught times t plus h minus, or no, plus d naught. That's just the top left corner of this, right? Then I have to say what? Minus all that stuff, right? So I'm out of room, but I'll just put minus 16t squared plus v naught t plus d naught, and then all of that divided by what? H. And I do not want to do that right now, okay? Because that's going to take too much time. But we could, right? And today is about finally getting something where we don't have to do the limit anymore, right? So we will come back to this, and we will use our rules today to do this instead of doing all this long work. But do y'all understand that the main point is that if you know where an object is at every point in time, you can always extrapolate what its velocity would be by just taking a derivative. And now, once I get that answer, if I wanted to know the acceleration, I would then do what? Take the derivative of that, right? So whatever answer I get out here is going to be a function, and then I take the derivative again, that'll give me my acceleration. So my acceleration will be equal to, it'll be negative 30, how do you know? Oh, you're already doing the shortcut from last time? Okay. Well, let's see what it'll be. Let's see. So what I wanted you to see here is that this is the second derivative. I don't know what it is yet, but it would just be the second derivative of the, oh wait, was it d of t? Yeah, d of t. Now remember, this is with no air, all right? Now, so if we have air on Earth, then why in the hell would we use this, right? Shouldn't you account for that a little bit? Well, here's the way things work. You start out with the very basic formula. This is a quadratic. Didn't we study quadratic functions a lot? I mean, we know a lot about quadratics, right? So what happens is in a physics class, what you do is you start first by saying, let's act like there's no air. And you try and work the problems out and you figure out what's going on. And then later on you say, let's add air. And so the formula now becomes more complicated. It's not necessarily quadratic anymore, but you can still do it and treat it the same way and work on it the same way you did this one. And then it's kind of like, you know, in physics, you start out by trying to move objects around. You act like there's no friction, and then later on you actually say there is friction. So same sort of story. We start off with something basic and then move it to something more complicated. As you probably are aware of, throughout history, science and religion have been at odds with each other for a long time, right? I mean, there was a point in time where they used to think that the center of the universe was the Earth, right? The Earth was the center of the universe, and everything went around the Earth, right? That was, and then someone came up and said, "Hey, no, we're not the center of the universe." And what happened to them? I don't know if they killed them, but they put them in jail, right? Well, when humans finally got to the moon, I don't know if y'all ever seen the video of the astronaut, you know, bouncing around on the moon, and he's got a feather and a hammer. Have y'all seen that? He drops them, and they both right to the ground. That was kind of like the scientists already knew that this formula worked, right? But people didn't buy it or whatever, and you know, wanted to discredit the science and the math. So when they got to the moon, it was kind of like see, we told you, like, look, they fall at the same, it doesn't matter because the moon doesn't have any air. So the air doesn't slow either one down. They both drop at the exact same rate. Anyway, the side note. All right, so our goal today is going to be able to find derivatives faster, all right, faster, much faster, and then come back and revisit a problem like this where we can say, all right, let's figure out what the velocity is without having to do all this, and then find out what the acceleration is, and then just kind of use those to answer some questions. Why would, let's think about this. Why would it be a good thing to know when the velocity here was 0? Think about if I take a pin, I throw it into the air. When is the velocity 0? At the highest point, right? Like it's moving, and it gets to the top, and when it gets to the top, just for an instant, it's not moving, right? So it's not changing position with respect to time, and then it comes down. So by somehow looking at the velocity and figuring out when that's 0, I might be able to figure out the point in time that it reaches the highest point. And then from that, I can actually figure out what that highest point was. Okay, but let's do today. Basic differentiation formulas. We're going to spend the next few classes talking about taking derivatives without the limit, all right? Without the limit. And what we start with is the most basic formulas for them, and then we get to more complicated formulas. Now, this is a very short set of notes. All right, here they are. I mean, that's pretty much it. Those are the notes for this section. I'm going to walk through them, and then what we're going to do is we're going to prove all of these. All right? then we'll start using them. The first one says that if you take the derivative of a constant, you should get 0. Derivative of constant should be 0. So let's prove these one at a time, all right? Does it make sense to you that the derivative of a constant c would be 0? We can just think about this geometrically. Someone give me an example of a function that is a constant function. F of x equals 2. Okay, if I plug in 2, this function looks like a flat line, doesn't it? Like this. Do we all agree that if you take that function and you pick some point on it and you say, what's the slope of the tangent line? We'd all agree that the slope of the tangent line would be 0. It would be flat. Because the whole function's flat, right? So the derivative at every point should be flat. But how could we prove it without the geometric proof? We would actually have to do, this derivative would actually have to be the limit as h goes to 0 of f of x plus h minus f of x over h, right? Which is the limit as h goes to 0 of, what's f of x plus h? Forget the 2 right here. Come back to this. It's just a constant function, right? So what happens if I plug x plus h into the constant c function? What does it spit out? What happens if I come over here and I plug in x plus h into that? What does it spit out? What if I plug in 5 into that? What does it spit out? 2? What if I plug in 10 into that? What does it spit out? 0? Doesn't matter what I plug in, right? That function only knows how to say one thing, right? 2. You plug in things, it just keeps on putting 2 out, right? That doesn't matter. So if I come over here and I say plug x plus h into that function, it's going to spit out that constant, right? No matter what. So it's just going to be the constant minus, now plug in f of x. So plug in x. Again, this function doesn't care what you plug in, right? So it spits out what again? 2, or in this case, c, right? So it spits out c again, all over what? H. But what's c minus c? It's 0. And what did I say happened if you ever get a limit and you have 0 on the top? I mean, this is 0, right? This is just 0. 0 divided by a number. Be careful here, though. Remember, I'm not saying the top is going to 0, right? The bottom is going to 0. What is the top? It is 0, right? There's a difference between going to 0 and being 0. The top is 0, so the answer here is 0. And that's why this first formula is true. So here's a specific example. Let's say I say f of x equals 10 to the e plus natural log 2. Find f prime x. What's the answer? Careful, careful. What's 10 to the e? It's a number, right? Plus natural log of 2. What's natural log of 2? A number. So what's a number plus a number? Is a number. So that's just a constant, isn't it? What's the derivative of a constant? 0. There's no other work to be done. Okay? Derivative of constant is 0. Now I made it an ugly constant to try and confuse you and make you not like it, but this is just a number. I may as well have put f of x equals 4 here. It's just a number. Now that's our first one. The next one is the derivative of x is 1. The derivative of x is 1. Now let me try something slightly different to kind of help you here. I'm trying to show that the derivative of x is 1. So please note that the function I'm trying to take the derivative of here is the x function, right? That's the function right in here, x. Let's set up the good old-fashioned derivative. The derivative is, the limit as h goes to 0 of f of x plus h minus f of x over h. Do you all agree with that? That's just the definition? Yeah? What happens when I plug x plus h into this function for x? What does it spit out? But if you plug in x, it spits out exactly x, right? If I plug in 2, it spits out 2. If I plug in 3, it spits out 3. If I plug in 5, it spits out 5. If I plug in x plus h, it spits out x plus h, right? It spits out whatever you plug in. So this is going to be limit h goes to 0. It's going to spit out x plus h, and then minus, now what's f of x? Just x, all over h. Now, do you see the x's cancel? And all you're left with is h over h, right? H over h cancel out and give you 1. What is the limit as h goes to 0 of 1? Well, does h do anything here? I mean, h goes to 0. What happens to 1? Nothing, right? 1 just stays the same. So your answer is just 1, which checks off what we were trying to show. Now, you could also convince yourself of this by looking at it. This is the actual function right here. We call this the identity function, f of x equals x. What's the slope of the tangent line on any point here? 1, right? No matter what. So it kind of makes sense that it would be that. All right, now the power rule. This is a big time rule today, all right? You'll be allowed to use this once we show it, and you'll be happy for it. We want to show that the derivative with respect to x of x to the n power is equal to n times x to the n minus 1. All right, first of all, the function that I'm trying to take the derivative of here is x to the n. Everyone okay with that? That's the function I'm trying to take derivative of, x to the n. So let me write down the definition. Limit h goes to 0. Okay, what happens when I plug in x plus h right here? What do I get? X plus h to the n. Minus what? Plug in just x, you get x to the n, all over h. And now we run into a problem. Because x plus h to the n does not mean you raise each one to the n, right? We talked about this last class. Do I remember last class? It was a long time ago. Remember this? Remember this thing? X plus h to the 0, x plus, I did this for a reason so I could come back to it today. There was a pattern that we identified, right? What I want you to notice about this pattern right now, something I did not point out last class. The first term in every single one of these lines, right, is exactly the x to that power, right? So if we did x plus h to the 7th, we'll get x to the 7th. X plus h to the 6th, x to the 6th. Yes? The second term from every one of these is always the number we had here, right? This is 7, so 7, and then the power on the x came down, the power on the h went up. Yes? So we have an x to the 6th h. Here we have a 6x to the 5th h. Here there's a 5, so 5x to the 4th h. Yeah? All right, and that would happen the rest of the way. Also, one more thing. We said no h's, then an h, then h squared, then h cubed. So the h's come up as we move across. Yes? Let's keep that in mind. I'm going to go back to today's. What I'd like to do is I'd like to try and write out this thing right here. Okay? I'm going to do it in blue. First, let me rewrite everything. Limit h goes to 0. Okay, x plus h to the n. Right? N is that power. So what's the first thing I'm going to have here? X to the n, right? Then plus n x, but remember, yeah, the power comes down, right? So what's 1 less than n? N minus 1. But you said h is there now, right? Correct? Do y'all see that? So like if that was x plus h to the 7th, it would be x to the 7th plus 7x to the 6th h. Yes? And then we keep going, right? I have to keep writing all this crap out. But watch what I do. There's some number in here. That number I'd get from Pascal's triangle, wouldn't it? I'd get that out of Pascal's triangle. I don't care about it. And then this x, the power on this has now come down again. So could I put n minus 2? And then didn't the h come up? So can I put h squared now instead? Questions? Questions? That's right. Okay, a great question. So how about I do this? Plus dot 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 plus, what's the very last one have to be though? H to the n. Now you can go back again to last class. Remember that last one, h to the 7th, right? So the first one is x to the 7th, the last one is h to the 7th. First one up here is x to the 6th, last one's h to the 6th, and so on and so forth. You all okay with that? That's just this part, right? Now what do I have sitting next to this? Minus x to the n, right? That's just this. Then all of this over what? H. Okay, do you see the cancel? What cancels here? X to the n minus x to the n are gone, right? What is it that we're trying to get to happen here? Trying to get an h to cancel, right? But do you see the x to the n's are gone? Okay, does this have an h in it? Does this one have an h? Okay, does this next term have an h? Actually, it has two of them, right? Does the next one have an h? And they all have h's, don't they? All of these have h's. They keep on coming up. So every single one of these has an h all the way to the end, right? So they all have an h. So would it be okay if I factor a single h out? I have an h in every one of them, right? So I can pull one h out. That's what I'm going to do. So this is equal to the limit. H goes to 0. I pull one h out. Tell me what's left when I pull an h out of this one. N x to the n minus 1 is still there, right? But no more h. Plus this one, the x to the n minus 2 is still there, isn't it? But how many h's do I have now? It was h squared. It's now h plus, now every single one of those you said had an h in it, right? So I could keep pulling them out. So I know that all those guys are still there. I don't care what they are. My last one is now h to the what? N minus 1. Because I took one h away from that last one, right? That very last one got one h taken away. So whatever the power was, it came down by 1. Is there anything else left out there? No? All of this divided by h. What happens to those h's? They cancel out. And now take the limit. Let h go to 0. What happens? What happens to this one? Do you see an h there? No. So it stays. Nothing happens to it. What about this one? It has an h there, right? That goes to 0, kills all that off, doesn't it? Every single one of these has an h in it, doesn't it? Every single one. So they all vanish. They all go to 0, except that one. So this goes away. They all go away. They all go away, all the way to the end. So the only thing left is n x to the n minus 1. And that's the formula. Apparently, I think that's a lot cooler than you do. You like that? That's pretty awesome, right? No? Now let's see how we can use it. As an example now, if you have f of x is x to the 5th power, then the derivative of that is what? 5x to the 4th. And you're done. Right? So all we're doing is what? Like I'd shown you before, it'll be real quick. We pull the 5 out in front, 5, and then we bring the power down by 1. How about this one? I'll use a different notation here. What if I take the square root of x and then I put a prime on it? That means I want you to take the derivative of this, all right? Just showing you a different notation for saying take the derivative. Well, is that x to a power? Is the square root of x x to a power? Yes. It's x to what power? 1/2. So n here for us is what? 1/2. So when I take the derivative will be equal to, the 1/2 comes out, right? X to the 1/2 take away 1, which is negative 1/2. Right? If you have 1/2 and you take 1 away, you get negative 1/2. So this is 1/2 x to the negative 1/2. But we don't like negative exponents, do we? We like to write positive exponents. So that means we should take that and drop it down, right? So this should be 1/2 times 1 over x to the 1/2. Y'all still following me? What is x to the positive 1/2? It's the square root of x. So isn't this just 1 over 2 times 1 over the square root of x? And isn't that just 1 over 2 root x? Just put them together? Yeah? This one, I think you should burn into your memory, all right? Because in this class, it's going to come up a lot that we're having to take the derivative of the square root of x. And every time we take the derivative of the square root of x, you should not go through this whole process. You should just remember that the derivative of the square root of x is 1 over 2 root x. 1 over 2 root x. So it just basically drops down, a 2 gets stuck in front of it, and you're done. You can, but so many times it's more useful for us to convert it. Any of these would be correct, okay? This would be correct, this would be correct, this would be correct, this would be correct. But if you go straight to this, later on, the problems are going to become easier for you. Here's another one. What if you have, I give you 1 over the cube root of x. I ask you to take the derivative. Is that x to a power? Okay, what power? 1/3? 1 over x to the 1/3, that's what cube root means? Do y'all agree with that? Now, can I use the power rule yet? No, okay? The power rule you can only use when you have x to a power. You cannot use the power rule when you have 1 over x to a power. So the first thing I have to do is write this as x to a power. What is that? X to the negative 1/3. Understand? That's a critical step right here. You cannot apply the power rule until you've written it as x to a power, even if that power turns out to be negative. Now, what? Now go ahead and use the power rule. So this will be equal to, the negative 1/3 comes out in front, x to the negative 1/3, and I'm supposed to subtract 1 from that. You need to start getting quick with your fraction stuff. Negative 1/3 minus 1 is the same as negative 1/3 minus 3/3, which is negative 4/3, isn't it? You might need to go back and start working on this whole fraction stuff, you're gonna be subtracting 1 from a lot of things, and if they're fractions, you need to be pretty quick with it. So I should have what as my answer? Negative 1/3 x to the negative 4/3. But again, we don't like negative exponents. Even though this is correct, it's not wrong. I could write that as negative 1/3 times 1 over x to the 4/3. Can you write that in radical notation? It's 3, and then what root is it? Cube root of x to the 4th. That's what x to the 4/3 means. The 4 is the power on x. The 3 in the denominator is the root. Can you even go further than that? The cube root of x to the 4th. Doesn't that mean how many groups of 3 are in here? It's one group of 3, right? So you could actually pull a single x out. And write it that way. You should be comfortable with all of these notations. This, and this. You should be very, very comfortable moving from one notation to the other. I want you to try one. I want you to try and figure out what 1 over the square root of x is. What's the derivative of that? Do that one on your own right now and see what you get. Everyone write it down because I'm going to take it off the screen. What is the derivative of 1 over the square root of x? Y'all getting somewhere? This what I'm putting up here is not what you're supposed to do, okay? How many of you are done? Raise your hand if you're done. Okay. Okay, now show of hands. How many are there yet? All right, so let's do it real quick. This first you have to rewrite it as what? 1 over x to the 1/2, and then you can go and rewrite that as x to the negative 1/2. And now you can use power rule, right? Negative 1/2 comes out. X to the negative 1/2. What's negative 1/2 minus 1? Negative 3/2. But that's the same as negative 1 over 2x to the positive 3/2. But that's the same as negative 1 over 2 square root of x cubed, right? But then when you take square root of x cubed, you do have one group of 2 in there, right, that you can pull out? So you can rewrite it as negative 1 over 2x root, what's still there? X. And you're done. So that took about, I don't know, 20, 30 seconds. Everything I wrote here was to remind you of the way we used to do it. Right? You would have to do f of x plus h minus f of x. Then you would get a common denominator. Then you come in with the conjugate. You'd multiply through. Things would cancel. You plug in. And you do all that. And at the very end, I get negative 1 over 2x root x, which is exactly the same answer. Much less work, right? Now, so the challenge for you, you're going to have to keep track of these numbers, right? Like making sure you're very meticulous with all the little, what's negative 1/2 minus 1. You can't mess that up. You mess that up, it's all over, right? Any questions on that? Sure. All right, next rule. Constant multiple rule. This is a really important rule. It gets kind of understated sometimes, and students kind of take it for granted. This says if you're trying to take the derivative of a constant times a function, then what you can do is put the constant on the outside and then just multiply times the derivative of the function. Now, be very careful. What's the derivative of a constant? 0. But if you attach that constant to a function, it doesn't go to 0. It stays with you. All right? Now, I'm not going to prove this one. I'm just going to show you how it's applied. So here we go. What if I give you a function f of x equals 2 square root of x? Find the derivative. All right, so do you see that now instead of just having square root of x, I have a constant in front of it being multiplied? Yes? Constant being multiplied times a function. So you want to kind of look at this as being your constant times, now this is your function. According to the constant multiple rule, all you have to do is just bring your constant down to the answer. The 2 will be here. Times, now, go find the derivative of what was there. So the 2 doesn't get touched, right? It just stays there, comes with you, and then just go find the derivative of the square root of x. What's the derivative of the square root of x? I just told you you need to burn that in. 1 over 2 root x, right? Now, what would happen with that 2 and that 2 down there with the root x? They would cancel, wouldn't they? And so you'd just be left with 1 over root x. Agreed? Here's another one. What if f of x was equal to 3/5 x to the negative 5? What is the derivative? Well, 3/5 is a constant, right? So I'm just going to bring it with me. then multiply it times the derivative of x to the negative 5. Now, x to the negative 5, I can use the power rule, can't I? So what's going to happen is I'm going to take the negative 5, I'm going to bring it out in front, right? So that'll be times negative 5, and then x to what power? Negative 6. Be very careful there. You have negative 5 and you're taking one away, right? Take one away from negative 5 becomes negative 6. What else happens out there? This one's down on the bottom, right? This one right here is up on the top. It's like over 1, so they cancel out. Except you have a negative 1 there still, right? So you would get, what number was still out there? Negative 3 x to the negative 6, right? Could I rewrite that as negative 3 over x to the 6th? Is that the same thing? Yes. Any of these answers are good, but you should just be used to, like I said, moving back and forth between them. Any questions on this? How about this one? F of x equals negative 4 over x. What's the derivative? What are you going to have to do here? Yeah, make this x come up, right? Get it out of here. So bring it up. It'll be x to the negative 1. So this will be negative 4 x to the negative 1. And now can you apply the rule? Yeah? Now the negative 4 is not going to get touched, right? So I'm just going to rewrite the negative 4. What's going to come out in front of the negative 1 and then x to the negative 2? Now what is really happening here technically is that the negative 4 is not changing, right? It's staying. The negative 1 is going to come out and multiply it, right? So in the end of the day, it's really going to just turn into a positive 4. And you'll start to get used to that, and you'll just start doing it in your head. Like, this is going to be 4, right? Be positive 4, x to the negative 2. But if you need to in the beginning here, write it out, write it out. Positive 4, x to the negative 2, which I could also rewrite as 4 over x squared. Yes, that's right. Trying to show you something important here. Where was it? 2? Yeah, this is a problem. This is I like to always show you all Cal 3 problems. I don't know why. But this is a problem in Cal 3 where they're doing some. We're going to learn this right here this semester. Not all. Don't worry about all the weird looks. But right now, you see this 1 over t right here? See that 1 over t? If I said take the derivative of 1 over t, you would rewrite 1 over t as what? T to the negative 1. And then you would apply the rule, right? The negative 1 would come out. You'd have t to the what? Negative 2? Is that it right there? That's the same thing? Right? That's negative t to the negative 2 with the t to the negative 2 drop down. I'm just showing you that in this huge problem, just there to there, that one little step is what we're doing right now. It's just a little piece of a bigger problem later. But it's an important, important rule. All right. Now, the only thing left for you to do with this is to practice and practice and practice until it starts becoming automatic. I mean, you got to do hundreds of these problems for you to start feeling really comfortable with it. So we move into the next rule, the fifth rule, the sum and difference rule. This is a really great thing about derivatives. If you're trying to take the derivative of some function plus some other function, so you have two functions side by side added together or subtracted, that you are allowed to break them up and do the derivative on each one individually. And that's a great thing. I will show you an example of this, right? Sum and difference rule. So let's say that I have a function, d of t equals negative 16 t squared plus 40t plus 13. I would like for you to find d prime of t. How many terms does d have, the function d have? How many terms? 3. 1, 2, 3, right? Terms are separated by addition and subtraction. Agreed? What that fifth rule says is that if you're trying to find the derivative of a function that has addition and subtraction between them, you just do each one of those, the derivative of each one individually, and just add the answers together at the end. So for us, what is the derivative of negative 16t squared? So the 2 would come down, hit the negative 16, become negative 32. The power on t would become just 1, right? So t to the first power. Y'all clear on that? Any questions how I got from there to there? Okay, the next one. What's the power on this t right here? 1. 1 comes out, so you get 40. T to what power? T to the 0. What's anything to the 0 power? 1, which means it's not there, right? Do you remember how we said the derivative of x was 1? Yes? Well, the derivative of t here, forget the 40 because it's a constant. So I'm covering it up. What's the derivative of t? It would be 1. So it just gives you 40 times 1, which is just 40. Understand? So that's this part. And then finally, plus, what's the derivative of 13? 0. You wouldn't need to write that. I just want to make sure you saw it. Negative 32t plus 40. Understand? What's the derivative again? What's the second derivative? Okay, negative 32 is a constant, but it's attached to the t, right? What did we just say the derivative of t by itself was? 1, right? So that would leave me with negative 32. And then 40, what's the derivative of 40? 0. And so that's all that's left. Now, believe it or not, this is the problem I started today with. This right here, right? Remember this? I said if I give you a number V naught and T naught, so V naught and D. D naught was where I was going to hold the object up, right? And then V naught was the initial velocity. So what I just did was I plugged in for height 13 feet. So I'm holding this thing 13 feet off the ground. I'm going to launch it with 40, which means I'm going to launch it straight up at 40 feet per second. All right? Oops, that didn't really work out. 40 feet per second. It's going to go up. It's going to come back down, and that be it. The first derivative is actually the velocity, isn't it? And the second derivative we said was what? Acceleration. Notice something about the acceleration. Does the acceleration have t in it anymore? No? That acceleration is the acceleration of gravity. It has nothing to do with time. As soon as you let an object go, the only force acting on it is gravity. So the acceleration should always be the same, constant, negative 32 feet per second per second. All right. How about this one? This is a classic exam type problem. When you get to problems on the test where I start to let you use the formulas, this is a perfect example of one of the first problems I would give you. So this would be considered an easy problem on the test. All right? I'm going to write it a little different just to give you some notation. Y is equal to square root of x minus 4x squared plus 3 cube root of x all over x, let's make it 3x to the fifth. Find y prime. What this problem is designed to do is to make sure you understand the power rule. That's all this problem is there for. Do you understand how the power rule is applied? Well, the first thing we have to realize is that to use the power rule, you have to have x to a power by itself sitting there, x to a power. Now, you are allowed to split things up, like in the previous problem. You are allowed to split them up into different terms and then do each one. That's okay. Now, we can't do it here, though, because even though these are split up, the whole thing's divided by this, right? So you can't quite do it yet. You have to do one thing first. What? Yes, in some way you can bring this to the top. If you have a single term in the bottom and multiple terms on top for a fraction, what can you do? Break it apart, right? So I can rewrite this. I'm rewriting. I'm not finding the derivative yet. I'm rewriting this as the square root of x over 3x to the fifth minus 4x squared over 3x to the fifth plus 3 cube roots of x over x to the fifth. Do you all follow that logic here? No, I'm missing a 3 on the bottom there. I could only do this because I have a single term on the bottom, right? That's the only reason I could do that. If I had two terms down here, we'd be screwed. All right? And we will have a way of doing that, just not yet. We couldn't do it right now. Now, for each one of these, I'm still not taking the derivative. I need to rewrite this as x to the 1/2 over 3x to the fifth minus 4x squared over 3x to the fifth plus 3x to what? 1/3 over x to the 3x to the fifth. Now, why do you think I did that? Yeah, so now what I'm going to do is I'm going to put this x to the 1/2 together with x to the fifth, this x squared together with x to the fifth. I'm going back to like college algebra basic exponent rules here, right? If I have x to a power over x to a power, what do you do with the powers? Subtract them. Still, I'm not doing any calculus yet, right? This is all algebra. Moving things around, x to the 1/2 over x to the 5, or fifth power, is x to the 1/2 take away 5. What's 1/2 take away 5? So how are you going to do that? I'm taking 1/2, I'm taking away 5, that's 1/2, I'm taking away 10 halves, right? And that's what? Negative 9 halves? Negative 9 halves. Just this piece right here turns out to be x to the negative 9 halves. What about this 3? What the heck do I do with that? It's going to stay there, right? It's going to stay there. Is it okay if I write it like this? Can I write that 3 on the bottom as a 1/3? Excuse me. Whoa. And then I can write these two, you said, as x to the negative 9 halves. So I can put x to the negative 9 halves. Is that fair to do it like that? I don't know if you remember. Hopefully, when you were in college algebra, your college algebra teacher told you that in higher level math, we don't like radicals anymore. We like to always write things in rational exponents. And this is why, because in rational exponents, you can apply the power rule. Right? If you leave it as a radical, you can't use the rule. Any questions on this? Have I taken the derivative? No, I still have not taken the derivative. I'm going to do this one now. What's that one going to be? X to the second over x to the fifth is x to the negative 3. And I'll write the 4 over 3 out there like this. And what about that last one? X to the... You should have thirds. What's 1/3 take away 5? Negative 14/3? What's in front of this? 3 over 3 is 1, so can I just put plus? Are you sure there aren't any questions? This is like a guaranteed problem on the test, so I want to make sure there's no questions here. Not this exact problem, but you know what I'm saying. Now can you do the power rule? Yes, because now you have 3 nice separated terms, right? Right there. 3 terms, you can do derivative on each one. All right, let's work with this first one. So watch my notation. I'm going to write y prime. That means the derivative is, okay, this negative 9 halves comes out and multiplies times that. What happens when you do negative 9 halves times 1/3? Negative 9 halves times 1/3, right? I'm multiplying. That's what? Negative 9 over 6, which reduces to become negative 3 halves, right? So I'm going to have in front here negative 3 halves, x to what power? Well, you take negative 9 halves and you subtract 1. Careful. It's negative 9 halves. Take away 1 is negative 9 halves minus 2 over 2, which is a negative 11 halves. You thought fractions were done, huh? You have to learn fractions in calculus. There's no way around it. You have to be comfortable with them. Negative 11 halves. That's our first derivative right there of this one. Now we move along. Here, I have negative 4/3. I'm going to multiply it times what? Negative 3. So I have a negative and a negative is going to become positive, right? In fact, those 3's are going to cancel each other out. So what am I going to be left with there? 4, x to what power? Negative 4. Next one. Negative 14/3 comes out. Does it hit anything? No, a 1. So how about I put negative 14/3 like that? X to what power? Negative 17/3. And I'm just going to leave it like this. You could continue to clean this up. In other words, you could drop this negative exponent down. You could drop this negative. You could drop all the negative exponents down. You could convert it over to radical notation at this point. That's our first derivative. This first test, that would be okay. Well, the thing is, eventually what we're going to be doing is we're going to be setting these things equal to 0. Like, is an equation equal to 0. So we need to be able to really manipulate them. Any questions? Yes. Negative 11 over 2. Remember, this came out and hit this, right? And that gave me this. Were you okay with that part? Okay, then I subtract 1 from that, right? That's what the power rule says. Subtract 1. So you take negative 9 halves and you subtract 1. It's the same as taking negative 9 halves and subtracting 2 over 2, common denominator. And then negative 9 take away 2 is negative 11. You do not have to. Now, the reason why sometimes it's okay to leave them is because what if I ask you to take the second derivative now? It would be so much easier to work with this, wouldn't it? Because it's ready to go. Like the next derivative, you bring the negative 11 halves out, subtract 1. You'd bring the negative 4 out, subtract 1. You'd bring the negative 17 thirds out and subtract 1. So it's just, if you do your homework and you check in the back of the book, their answer may look completely different than yours, but you may have the exact same answer. So you need to make sure that you're like, oh yeah, I see, all they did was just dropped it down. And understand? Okay, what about this one? How about if f of x equals x squared plus x plus 1 squared? Find dy dx. So I'm mixing up the notation again, just so you can, you know what, let me change that f of x to y. Y equals this, find dy dx. Yeah, see, good call. Look, our power rule works if we just have x to a power, and then we could also have it separated by different terms. We can handle that. But this one, even though these are 3 terms, the whole thing's being squared. You can't just go in there and say, I'm going to do a power rule on each one, just throw the squared on the answer. No, you have to actually figure out what this is first before you can apply the power rule. That means I have to actually square that. So on the side here, I'm going to do x squared plus x plus 1 times itself, x squared plus x plus 1. And when I do that, I expand x squared times x squared is x to the 4th. X squared times x is x cubed. X squared times 1 is x squared. Then I do x times x squared is x cubed. X times x is x squared. X times 1 is x. Then I have to do one more multiplication. The 1 times everything. So plus x squared plus x plus 1. I'm trusting that you could expand that on your own. Now collect all your like terms together. What do you get if you collect all those like terms together? X to the 4th plus 2x cubed plus 3x squared plus 2x plus 1. Sounds good to me. So that's what that is, right? This expanded out is this. So can I do what we call term-by-term differentiation? Term-by-term differentiation. Can I do term-by-term derivatives? Term-by-term differentiation, yes? Yes, right? Because we have a bunch of terms now, right? Nothing's out there outside of this raising into a power. We don't have any fractions like we did in the previous problem. So I just take derivative of each one of these, one at a time, and put those in my answer. So what is the derivative of x to the 4th? 4x to the 3rd. What's the derivative of 2x cubed? 6x squared, so plus 6x squared, right? What's the derivative of 3x squared? Plus 6x. What's the derivative of 2x? Just 2, right? What's the derivative of 1? 0. That's my derivative. How do you feel? All right. We can pretty much handle x to powers now with this rule. And there's a lot that we can take derivatives of now and using this shortcut. But we still have a lot of limitations on what we can handle. So what we want to look at now is what is the derivative of the sine function? It's cosine? Why? Oh, I did? When did I show that to you? It's in your notes, right? It's here. You already saw it right here, right? That's what we have. We have now additional rules for derivatives. Now, I'm going to show you one of these and only one, and then I'll come back here, and we just have to memorize these, okay? In my Cal 2 class, first day of class, I gave them an 8-question quiz, first day of class. The first question was, what was the derivative of sine x? That's the first thing I asked them. This has to be hardwired. Like these first 3 have to be hardwired. They come up so much. These others, you just need to know they exist, and you need to know where on your formula sheet you can get them. And if you do enough math, if you have to take Cal 2 and Cal 3, then these will get hardwired eventually. But the first 3 here, numbers 6, 7, and 8, got to be in there. All right? And of course, the power rule has to be there also. You should not need to refer to a formula sheet for the power rule. Just remember the number comes out, subtract 1. Number comes out, subtract 1. Okay, I'd like to show you that the derivative of sine x is cosine x. And once I do this, that'll probably be it for the day. All right, the only way to show this to you is to take the limit as h goes to 0 of f of x plus h. So what happens if I plug x plus h into this? I get sine x plus h, right? All right, and then minus f of x, which would be sine x, all over h. Now, everyone in here should have taken pre-cal, so I'm going to use something from pre-cal that you may or may not remember. But let me tell you one thing. This right here is not sine x plus sine h, okay? That is not true. Sine is not a number. It does not distribute through the parentheses. X plus h is the argument of sine. Therefore, this little thing of distribution is like a major, major, major no-no, all right? However, we do have a formula for sine of the sum of 2 angles. See if you can find that on your formula sheets. I allow you to have formulas on your test, right? Yeah, I let you have something on the first test, right? If you go to the sheets that I have for you, on reference page 2 under trigonometry, on the bottom right-hand corner, not far right, about midway up the page, says addition and subtraction formulas. And it tells you what sine of x plus h is. For us, sine of x plus y, we're going to be replacing the y with h. And so that formula is sine x cosine y, so for us cosine h, right, plus cosine x sine h. All that is this. Okay? Y'all buy that? From pre-cal, that's what that is. Now what do I still have up here? Minus sine x all over h. Wait a minute, hold on. I'm supposed to get an h to cancel, right? I'm supposed to get an H to cancel, but these H's are trapped inside these trigs. I can't just cancel those, right? So watch what I'm going to do here. This is the limit. H goes to 0 of, do you believe this? Sine x cosine h minus sine x all over h plus cosine x sine h over h. Do you believe that? All I did was move this sine x right here next to this, move this one over here to the side, and then put them both over h, which is allowed, because if I split fraction up, I can put it back together, and I would have this, right? Okay, so that's fair, that's legal. Now remember, in this limit, the only thing that's changing is h, isn't it? The x is not changing, the h is. So I'm going to factor out of this first one, they both have a sine x, right? If I factor a sine x out, I'll have this. Limit h goes to 0. I'll have sine x. Now, what will be left there is cosine h minus 1 over h. And then on the other one, I'm just going to put the cosine x out front. Sine h over h, like that. So I pulled the sine x out of both of those and just dropped it in front. And if I distribute it back through, it would go back to both of those and be the same thing. And then over here, the cosine x, I just pulled it out in front like this. Do you see why I did that? Let h go to 0. Yes, good. This right here, sine h over h, is the sine of junk over junk, isn't it? This is junk. This is junk. They're the same. They're both going where? To 0. So that should go where? To 1. This right here is going to go to 1. Times, what's still in front of it? Cosine x. Now this one, we did not talk as much about that. Do you remember that quiz I gave you? Remember that quiz I said, hey, look, in the video lecture, there were 2 formulas that you were supposed to know. You remember that? Know these formulas. I gave you a quiz, said, just give me one of them. This is the other one. That one goes to 0. And since that goes to 0, and that's sine x out in front of it, and you're adding these together, your answer is what? 0 plus cosine x, so your answer is cosine x. Cosine x. So the derivative of sine x is cosine x. Done. That's proving it. All you have to do is remember it, all right? The other ones you need to know, the derivative of cosine x is not sine x, it's negative sine x. What happens if you forget that negative? Well, you're wrong, right? Here, sine x derivative is just cosine. That's fine. The other way around, you get a negative that pops in there. What's the derivative of tangent x? Secant squared x. Ooh, that one you're just going to have to remember. Derivative of cosecant x. Negative cosecant x cotangent x. Derivative of secant x. Secant x tangent x. Derivative of cosecant x. Negative cosecant x cotangent x. Derivative of cotangent x. Negative cosecant squared x. It's just all at some point has to be in there. Like I said, for a class like this, Cal 1's the end of the road for you. 6, 7, 8 should be up here. Cal 2, Cal 3 is in the future. Just get them all in there as soon as possible. All right? There's a pattern to these. I don't know. I mean, it's a little pattern. Figure out whatever pattern makes sense to you. I have my own pattern, the way I remember it. But wanted to show you one last thing. I know you want to get out of here. This is y equals sine x. Okay? I'd like for us to graph its derivative. Graph its derivative. Well, what is the slope of the tangent line right here? 0. So if I go down here, the derivative should be 0 here, right? What about right here? What's the slope of the tangent line here? 0, so the derivative should be like this, right? What does it appear to be at this point? I have to do it kind of in red here at the beginning. Y'all see that? That slope looks like it's about 1. It is, actually. And then right about here in the middle, the slope here is actually about -1 exactly, all right? Which is down here. And then the slope right here at the very end is actually, again, 1, which is up here. And then let's talk about the slope of the tangent line somewhere like right around there. It's not quite 1 anymore, right? Like this was 1. As I move this way, the slope of the tangent line is what? It's still positive, but it's getting closer and closer to 0. So this should actually go something like, it should be big and then it should get closer and closer to 0, shouldn't it? And then as I move around on this side, I should have negative values that start small but get closer and closer to -1. So it should come down like this. And then when I go the other side, it's going to follow the same pattern. And then when I come up the other side, same pattern. Well, what the hell is that? That's cosine x. You see that? Here's sine x. Its derivative is cosine x. It's a connection you never saw before, but that's how they're related to each other. The derivative of sine is cosine. Now, the other way, it works opposite. If I sketch cosine, right, then let's start. Okay, this is cosine x. Let's see. Right here, what should the slope of the tangent line be? Okay, what should the slope of the tangent line be here? 0, so that should be down there. Up here, slope of tangent line, 0. All right. What's the slope of the tangent line right about there? -1, right? So it should be down here. What's slope tangent line here? +1. And then if you follow the same patterns, what you'll realize is that it's doing this, and this, and this, and this. Now that's not sine x, is it? But it's sine x flipped over. So it's negative sine x. And again, there's the connection. Now it becomes a little more complicated when you go into the other trig functions, like tangent and how it's connected to secant squared. But with sine and cosine, it's somewhat relatively easy to see the connection between the function and its derivative. All right, for homework, I don't even know what the assignment says on your schedule, but let me just tell you what you should do. Do we have anything due next time? I didn't give you a take-home quiz or anything, right? Everything's good? Okay. All right. These problems are to be turned in beginning of class, next class. All right? What I'm going to do is I'm going to look at them and I'm going to hand them back to you. All right, I'm going to do a homework check because that's how important it is that you do this homework. Problems, this is page 105. I want you to do 1 through 25 odd. All right. And then 2 through 26 even for bonus. Why don't you just say 1 through 26? So what I'd like for you to do is when you come in, I would like for you to turn in, have all the odds prepared on a single sheet of paper or multiple pages. If you do the evens for bonus, I'd like for you to do those separately. All right? And that way I can really look at them and they're not all mixed up and I'm trying to figure out how many odds and evens you did. All right? That's to be turned in next class. So that's what, about, 12, 13 problems? All of those are power rule and sum and difference that we just did today. All right? So use the rules. Y'all have a great day. Should we take attendance? No. Who's not here? Damn it. All right, I already have it in my hand. Let me call it. It's not 2:40, so I'll start at the end of the alphabet. It's today 29. Okay, honors here. Mark. Did Mark show up? Okay, Mark. Caroline. Anthony. Jean-Luc. Ruben. Leon. Mark Pena. Mark. John Pena. Oh, there you are. Ernest Ortiz. Okay, Aurora. Sean. Paul. Elizabeth. Kyle. Tamika. We're going to meet, right? Alexis. No Alexis. Jorge. Brooke. Ellie. No, Lily. Yes. Tyler. Rodrigo. Aaron. And Kevin. All right. I miss anybody? Okay.